Hello, and welcome to Lecture 2 of the Interactions unit in Phys 1104. In this lecture, we're going to take our newfound knowledge of interactions and use it to figure out things about different types of energy. We're going to meet potential energy and energy dissipation, and by the end of the lecture, we'll have a classification scheme for types of energy. We saw at the end of the last lecture that even during elastic collisions, there's a conversion of kinetic energy into internal energy during the collision, while the colliding objects are interacting with each other. And in particular, right around the midpoint of the collision, there's a moment when the two objects are moving at the same velocity, and that corresponds to the moment when the total kinetic energy is at its minimum. We can get some more insight from this, and to do so, just think of what it looks like if we cover up the after the collision portion of the picture. Now that during collision part looks just like the end of a totally inelastic collision. And when I say just like, I mean if we're comparing collisions with the same inertia objects, starting with the same initial velocities, then conservation of momentum dictates that the velocities in the middle of the elastic collision are exactly the same as the velocity at the end of the totally inelastic collision. And so they must have the same total kinetic energy. And so comparing the total kinetic energy versus time for an elastic and a totally inelastic collision, you'd see a graph that looks like this, where the histories of the kinetic energy look the same up until the midpoint of the elastic collision. And remember that what's going on here is that kinetic energy is being converted into internal energy, so that we can say that the internal energy at the middle of the elastic collision is identical to how much internal energy the system has at the end of the corresponding totally inelastic collision. But hang on, from the previous unit, we know that in a totally inelastic collision, the amount of internal energy you end up with is equal to the convertible kinetic energy. And so that's also true for an elastic collision, that at the midpoint of the elastic collision, all of the convertible kinetic energy has become internal energy. The difference, of course, is that that conversion in the elastic collision is reversible, and it all gets converted back into kinetic energy. Whereas for the totally inelastic collision, that's an irreversible change. Adding the internal energy versus time onto the graph, we end up with an energy versus time graph that looks like this. And we could also show energy bar charts for before, middle, and after, showing the internal energy converted in the middle, but eventually returning to the kinetic energy. Notice that this internal energy is sort of special. It can be converted back into kinetic energy, or you might say it has the potential to convert back to kinetic energy. And it's for that reason that we call it potential energy. And we represent potential energy with a capital U. Don't ask me why, except I'll say that the capital P was already taken for things like pressure. Please keep in mind that potential energy is just one type of internal energy. Not all internal energy is potential energy. The thing that makes potential energy special is that you can get it back. You can convert it back into kinetic energy. And so in that sense, it's often referred to as stored energy, which raises the question of where it's stored. Well, the short answer is that it's stored in the configuration state of the system. What the heck does that mean? It means that it has to do with the spatial arrangement of objects in the system which interact with each other. And notice I've highlighted a bunch of words in that statement because they're all important. Let's think about two carts interacting via a spring. You probably have a sense that when the spring is compressed, there's some spring potential energy, and if you compress the spring more, then it has more spring potential energy. But it's also important that to even define spring potential energy in the system, the spring and both carts that are interacting with it also have to be in the system. Otherwise, this isn't an energy that's in the system, it's something to do with the system's interaction with the environment. And it's also only dependent then on the relative position of the carts, because it's the relative position of the carts that determines how compressed the spring is. It can't depend on the positions of the carts with reference to some arbitrary axes, because then the potential energy would depend on how you define your axes, and that doesn't make sense. It should only depend on the length of the spring. For example, when a golf ball is hit, the golf ball compresses like a spring. You can't notice it unless you watch very high-speed film, but it's behaving exactly like a spring, and so you get spring potential energy during the interaction between a golf ball and a golf club. Potential energy is just one kind of internal energy, but it's also itself a broad classification, and there are many types of potential energy. There are two main ones we'll look at in this course. One is spring potential energy, which is also sometimes called elastic potential energy, and has to do with amounts of reversible deformation of objects. The other type that we'll spend a lot of time on is gravitational potential energy, and it has to do with the height of objects above the ground. But note that we have to include all the interacting objects in the system to be able to define a potential energy, and gravitational potential energy is to do with the gravitational interaction between objects and the Earth. So we're only allowed to define a gravitational potential energy if we've included the Earth in our system. Another one that we've really seen, but won't talk about much because it turns out to be rather complicated, is magnetic potential energy. We've already seen carts colliding elastically, therefore with reversible changes of state, using magnets, and so that tells you that there must be a potential energy associated with that magnetic interaction between the carts. However, in Phys 1204, one type of potential energy we'll look at a lot is electric potential energy, which of course has to do with electrical interactions, repulsive or attractive, between various types of objects. We've also seen that energy can be converted to internal energy in ways that are irreversible. When this happens, we say that the energy is dissipated, or we say that the conversion is dissipative. An everyday example of energy dissipation can be seen with something as simple as a piece of paper. If you take a piece of paper and bend it over without folding and then let go, it'll unbend itself, and you can do that in any direction you want, and you can do it as many times as you want, and the paper is left essentially unchanged. When you do this, you have stored potential energy in the paper. It isn't very much potential energy, but you can use it to get something moving as long as the thing is very light and you don't want to move it too far. Essentially, you've made yourself a little paper catapult. On the other hand, if you fold or crumple the paper, then the energy that you've just put into the paper can't be recovered. It has been dissipated into irreversible changes in the paper. To understand what's happening in bending paper versus crumpling paper, think at the atomic level, and a simple picture is that when you just bend the paper, then the atoms rearrange in fairly orderly ways with just a few stretches of bonds. We say that this rearrangement of atoms is coherent, which is just another word for orderly. On the other hand, when you crumple or fold the paper, you break atomic bonds, and atoms get displaced and form new bonds with different atoms in fairly random ways. Now the atoms can't get back to their original positions because there are other atoms in their way. We call this sort of rearrangement incoherent, which just means it's sort of random and disorderly. So irreversible deformations of objects involve incoherent rearrangements of the atoms in those objects. Just as the configurations of atoms in objects can be rearranged coherently or incoherently, it's also possible for the motions of atoms in an object to be coherent or incoherent. When an object moves, all of its atoms move together in a coherent way. They're all doing the same thing. On the other hand, the atoms in an object can have random, or what we call incoherent motions, where they don't all move together, they move in different directions, and this doesn't result in the object moving, it's just random internal motions of the atoms. Incoherent motions of the atoms in an object are a large part of why most collisions are inelastic. To see how, first think about this cart that's bouncing elastically through a magnetic interaction off of this barrier, and the whole cart moves as a unit with all its parts moving together. In contrast, now look at this collision between the cart with the barrier where the cart now has masses hanging off of it. During the collision, the masses are jarred into motion and swing around in a fairly disorderly fashion. The kinetic energy associated with the coherent motion of the cart, all moving together, is partly converted into incoherent motion of the masses, and so the cart rebounds from the barrier with a lower speed than it had before it hit the barrier. The incoherent motions of atoms in an object are responsible for the object's thermal energy, which is another kind of internal energy, but it's not a potential energy because you can't easily convert it back into kinetic energy. Objects with high thermal energy have high temperature, but be careful, thermal energy is not the same thing as temperature. Also, thermal energy is not the same thing as heat. I'd love to tell you more about these fine distinctions between thermal energy, temperature, and heat, but it gets very complicated, and so I'm going to say if you want to know more about these distinctions, you should take a thermodynamics course, or even better, my statistical mechanics course, which I teach sometimes. We now know enough about the different types of energy to set up a comprehensive classification scheme, and every type of energy that we will encounter will fall within this classification scheme. Broadly, we can divide energies into energies to do with motion and energies to do with configuration, or in other words, how things are positioned relative to each other. And we can also divide them between coherent forms and incoherent forms to do with how orderly the motions or configurations are. So coherent motion, or in other words, the motion of whole objects, is kinetic energy, whereas the bulk or object scale configuration energy is potential energy. Incoherent motions at the atomic scale give you thermal energy. We don't really have a good name for incoherent energy of configuration, but it's energy to do with irreversible deformations of objects. And everything except kinetic energy is what we've been calling internal energy. An important distinction is that conversions back and forth between kinetic and potential energy, or among the types of potential energy, are reversible, whereas it's very difficult to reverse any energy conversion from kinetic and potential into the incoherent forms. And because of that, we call the coherent forms mechanical energy because they have to do with bulk scale whole object motions as opposed to the microscopic scale things that incoherent energies have to do with. There's just one more type of energy we'll meet, and it's called source energy. It's an incoherent energy, and somewhat confusingly, it straddles the line between an energy of motion and an energy of configuration. We'll talk about it in the next lecture.